Ok. Eccola. Niente, dai, stiamo iniziando adesso. Ok, vedete la slide a casa?
Sì.
Okay, so let's start. So yesterday we started introducing the Higgs mechanism, which is the mechanism provided by the standard model to provide masses to the gauge bosons, so the weak interactions, the W and the Z, while keeping the photon massless. Okay, it's a quite complex mechanism. Okay, very elegant. And yesterday we actually introduced in different steps the concept of spontaneous symmetry breaking. Okay, where the Lagrangian maintains its symmetry, but the current state of the theory does not anymore. So we started with the simple case of a real scalar field. Then we moved to the more complicated case of a complex scalar field, okay, in terms of phi1 and phi2. And then we introduced the real Higgs mechanism that acts on the gauge theory of the Electroweak interaction, which requires 4 degrees of freedom. Okay, so let's start from here now. Let me just recap a few things before we go to the new part. So as we mentioned yesterday, the minimal Higgs model requires 4 degrees of freedom, 3 of which will become Goldstone bosons, so unphysical massless bosons that appear in the theory. And they have to be somehow dropped from the Lagrangian. And this is done through the unitary gauge, where the 3 degrees of freedom of the 3 Goldstone bosons are, as we announced yesterday, reabsorbed into the longitudinal polarization degrees of the massless, massive gauge bosons, W and the Z. Okay, these occur only for 3 of them, for the Z, W plus, W minus, but not for the photon, which in fact remains massless, as we know. There is an additional degrees of freedom, because we are starting with 4, and the remaining degrees of freedom does not take part to this unitary gauge. It remains as a free object. It is a scalar boson. It is called Higgs boson, and we need to observe it. Otherwise, the theory cannot be proved. So, in this minimal Higgs model, these 4 degrees of freedom are arranged in a weak isospin doublet, okay, where 2 complex scalar fields are put here. So, differing with 1 unit of electric charge. The phi plus on the upper part, which is phi1 plus I phi2, and the phi 0, which is the neutral part, given by phi 3 plus I phi 4. Now, this is the Lagrangian, okay, as we saw yesterday. So we have a kinetic term for the field, and then we have a potential energy term, which is given in terms of the field and its complex conjugation stage. Now, we want to evaluate the minima of this potential energy, so the 2 parting states of our fields, and so we minimize the potential. And in particular, we choose the solution with the mu square negative. Once we do so, we found that there is an infinite set of degenerate minima, so degenerate vacuums, which satisfy these, let me call hyper circumference. It is a circumference in 4-dimensional space, of course. Now, the field has to choose its own physical vacuum state among all the infinite possibilities. Once it does so, the symmetry is broken spontaneously, okay? And so at the end, the field just choose one of the possible vacuum states. Without loss of generality, let us take the vacuum state okay, where essentially the upper part of the doublet is vanishing, and the vacuum corresponds to the lower part. Okay? Then we want to create particles, so excitation, okay? So the field can be excited by introducing perturbation of the field itself around the minimum. And since we have 4 degrees of freedom, we have to introduce 4 different perturbations that we call Xi1, Xi2, Xi3, and H. Okay, so overall, our doublet, after the spontaneous symmetry breaking, looks like this. Okay, now it is the time where we apply this unitary gauge, this magic, if you like, where the 3 Goldstone bosons, Xi1, Xi2, Xi3, now disappear from our field because they provide now the mass to the 3 bosons, and we are left with just one object, one scalar boson, which is the Higgs boson. So this was our arriving point yesterday. So let's move on now. What we will be doing today is to derive step by step on the blackboard how these mass terms of the gauge bosons really show up in the Lagrange. Okay? È un'operazione un po' brigosa, ok? Ci va un po' di lavoro sulla lavagna, però credo che ne vale la pena, ok? Perché altrimenti questa cosa dell'X rimane una favoletta. Cioè, se la dico così, vabbè, è bello, funziona, ok, però è importante vedere anche come in effetti vengono fuori i termini di massa poi nella Lagrangiana, ok? È lì che c'è la prova teorica e poi quella sperimentale, ovviamente con la scoperta del bosone di Higgs. So, now, so the Lagrangian of the electroweak model must be symmetric, as you know, for this global gauge transformation, SU2 left, U1 hypercharge, okay? And this, as we saw yesterday, can be achieved by introducing these 4 gauge bosons through the covariant derivatives, the 3 W's and the B. Now, what about now the Higgs? Because we want to apply these to the Higgs, okay? So our goal is to apply these to this Lagrangian here, okay? So to our Higgs field. So about the Higgs, so since now, after symmetry breaking, the upper component of the doublet is 0, okay, and the lowest component has, by definition, the negative value of the third component of isospin, so -1/2, and also neutral electric charge, one can put all this information into the formula for calculating the hypercharge, the weak hypercharge. And so it turns out that the weak hypercharge for the Higgs doublet is +1, okay? So we can substitute this +1 here, okay, inside this term here in the covariant derivative. So once we do so, we can now apply the covariant derivative to the field, okay? So this is what we get from the covariant derivative, where now we put +1 instead of y, okay? And this is our Higgs field after spontaneous symmetry breaking, okay? So after the Barton has been chosen. Now, let me recall you again that this guy here is essentially corresponds to this guy here, okay? So we are now going to construct these Lagrangian step by step and to derive the quadratic terms, which are the mass terms, okay? So in order for this Lagrangian to be gauge invariant, we have to use the covariant derivatives in terms of the gauge fields, which are massless at this point. Now, we can put now everything together, okay? So this is the kinetic term for the Higgs field. Now we have this is the Higgs potential energy, okay? So this is the standard Lagrangian that I showed you before, but now with the covariant derivative instead of the standard derivative. Then we can add here also the Yang-Mills terms, so the kinetic terms for our gauge bosons, the W's. So these are 3 terms here and 1 term here for the hypercharge. And so we can actually split this Lagrangian into 3 main terms. LD, where D stands for the derivative, so this is the kinetic term. LV stands for the potential energy term, and L Yang-Mills for the Yang-Mills term. Okay. Now, as we will see today, the masses of the gauge bosons, so the W, Z, and the photon, and also the Higgs boson itself, because it is a massive scalar particle, will be determined by picking up the quadratic terms in this field that appear in our Lagrangian. Okay, so this is now our job. Okay. So as a first, so we have to determine what we have to find here. We have to find 5 things: the mass term for the Higgs boson, the mass term for the W plus, the mass term for the W minus, the mass term for the Z, and possibly the mass term for the photon, which is 0. So let's start deriving the mass term for the Higgs boson itself. And this we do by searching for quadratic term into the last part, the second part. The potential. So, vabbè, questo è già morto. Beh. Okay. So this is our potential energy, che anche questo è morto. Allora, le riserve. So this is in general mu square pi lambda, emission on the way, and then we have plus lambda pi lambda pi. So this is our energy potential term in the Lagrangian. So let's now substitute the expression of our Higgs field after that spontaneous symmetric breaking. So this is mu squared. Now we have 0 b plus h divided by square. And this is this guy here. Okay. Now we have this guy here. This is the vector. So this is 0 and then b plus h divided by square. This is the first piece, and then we have the second piece, lambda, again, 0, b plus h divided b plus h divided. Right. Okay, so these are now trivial vector-vector products. Okay, so this is 0 plus and this right here. So this is mu squared. We just take the square of this. So this is mu squared divided by 2, and then we have b plus h squared. And similar here we have lambda to the 4, which is 2 to the square, which the other is divided by 4, and then we have b plus h to the 4th power. And so really it is mu squared divided by 2, b squared plus 2, b h plus h squared plus lambda divided by 4, with b to the 4 plus 3 b h plus 2, right, plus 6 b squared h squared plus 3 b h cubed plus h. Okay. So the scope of our game is to find the mass term of the Higgs boson. So we are only interested in the quadratic terms in the Higgs field. Okay, for the rest we don't care. So one is here, and the other is here. So when we concern ourselves only to the quadratic terms, let's see, second order only. Okay, so we have just mu squared divided by 2 x squared, which is this term here, and then we have this guy here, so it is plus lambda 4 x b squared x squared. Now let me remind you that we can always express mu squared as minus lambda b squared. So we can substitute here. So this is going to be 1/2 minus lambda b squared h squared plus lambda to the 4. No, here we can have a sigma lambda b squared h squared. Now we can add those two terms because they are homogeneous, right? Lambda b squared x squared, lambda b squared x squared. And so the result is simply lambda b squared h. It's minus 1/2 plus 3/2 without 1. Okay. So this is now a pure quadratic term in the Higgs field. Okay. So in the language of the Lagrangian, this has to be of the form 1/2 mh. Okay. This is the way the mass terms appear in the Lagrangian. And so from here, we can finally derive that the mass of the Higgs boson is signified through Okay, this is our first result today. So lambda is just a parameter that enters into the Lagrange, okay, which essentially evaluates the strength of the 4-point self-interaction term. And D is the vacuum of the field, is the value of the field at the vacuum. It's the vacuum expectation value of the field, okay? So it's a number. All of this is a number, and numerically will correspond to the mass of the Higgs boson.
L'ultima mettiamo perché il termine di potenziale questo.
Come dici?
Dico l'ultima uguaglianza.
Questa qui? No, questa è generale, perché quando tu hai un termine quadratico in una lagrangiana di un campo scalare, questo termine quadratico deve avere questa forma qui. Basta confrontarti con la lagrangiana di Klein-Gordon, okay? Ha questa forma qui, quindi devono essere uguali, quindi uguali alla massa. Okay? Okay, we will comment later on this result. Let's now move on to the W and the Z masters. Okay, for the mass term of the gauge bosons, we have to look at the first term of the Lagrange here. Okay, so we have to begin now with this term. So let's start first of all from the covariant derivative applied to the Higgs field. Okay, so as we saw, this is 1/2, then we have 2 the move, and then we have the identity matrix. Okay, and we have plus Ig sigma scalar W, which are our 3 gauge bosons for the term SU2L, plus Ig prime, and then we have D move. Okay. Well, we already used the fact that the hypercharge for the Higgs is all this acting on our Higgs field, which is 1 over square root of 2, and then 0 B plus H. Let me recall you, okay, we'll not do this anymore, but this is a H of X field. So this is a number, this is a field, which is like the space-time coordinates. In general. So now, let me write it in a more explicit way. So we have 1 divided by 2 times square root of 2, that we put in here. Then we have twice the standard derivative and the identity matrix, 2 by 2, plus Ig. Here we make explicit the scalar product of the Pauli matrix with the bosons. Okay, we're here. Now we have the last one. G prime. Then we have the D. Just multiply the identity matrix. So, and then we have our Higgs field. So, to make it explicit, this is 1, 0, 0, 1. It is 0, 1, 1, 0. This is 0 minus I, 0. This is 1, 0, 0, minus 1. And this again 1, 0, 0, 1. So let's now work out all this. This remains. So now we have 2 the mu multiplying the identity matrix. So this is 2 the mu 0, 0, 2 the mu. This is the first step. Plus, now we multiply Ig times this Pauli matrix here. So this is 0, Ig W mu 1, Ig, oh, W move 1 and 0, and this is the second, plus 0, G W move 2 minus G W move 2 and 0, plus I G W move 3, 0, 0 minus I G W move 3, plus I D prime D move 0, 0 I D prime D move, acting on the Higgs field, the vacuum. Okay, let's now add all these three matrices and let's do it number by number. This is 100 divided by put the root of what we have here. To the move plus 0 plus 0 plus IGW3 plus IG prime D move. So what it is? The move plus IGW move 3 plus IG prime D move. And this is the first element of the family. Now we go to the second, 0 plus IGW1 plus GW2 plus 0 plus 0. So this is I, G, W move 1 minus I, W move 2. Now we have 0 plus IGW1 minus GW2 plus 0 plus 0. So this is I, G, W move 1 plus I, W move 2. And then we have to remove plus 0 plus 0 minus E derivative 3 minus E given 2 remove minus I G move 3 plus I G prime D move. Okay, all these acting on 0 D plus H. Okay, and now we have to multiply this matrix by this vector. Okay, so it is 0 times this plus 0 times that. So the result of this is 1 divided by 2 square root of 2. So the first element of this vector is I, G, W1 minus I, W2, multiplying with V plus A to X. And second is 2 the move minus I, G, W V plus I, G prime D move, multiplying again V plus A to X. Voila. So for brevity, let me just call these as 1 divided by 2 square root of 2 A and B. G. So this was the first term of the first term of the Lagrangian. So we have actually two derivative terms. So the LD Lagrange part of the Lagrangian is actually the mu phi dagger and the mu phi. So these are, in other words, 1 divided by 2, the root of 2 squared, and then we have a star, b star, that multiplies a b. Where now A and B are this object and this object. Okay? So let's substitute here. Andiamo qui. Allora, radice di 2 al quadrato fa 2, per 4, 8, 1, 8. Ah, ok, needs space. Okay. Now, A star is the complex conjugate of this term here. Okay? So wherever we have I, we have to put minus I, let's reverse. So this is minus I, G, W1 plus I, W2, B plus H, and then we have the B star, which is 2 the mu plus I G W mu 3 minus I G, the G prime, right? Yes. G prime D mu B plus H, and we are here, and now we have to put it in a vector. And so we have I, this is the second point. W mu 1 minus I W mu 2 B plus H and 2 mu minus I G W mu 3 plus I G prime B mu B plus H. Okay? Now, let's multiply. Let's have fun. So, we get 1/8. Then we have minus Ig and Ig is G squared. And then we have W mu 1 plus I W mu 2 B plus H times W mu 1 minus I W mu 2 B plus H plus 2 the mu plus I G W mu 3 minus I G prime mu B plus H times 2 the mu minus I G W mu 3 plus I G prime B mu B plus H. Ok, adesso abbiamo avere a che fare con questa brutta bestia. Let me remind you that V and V is just a number, okay, whereas H is a field, which is a function of space-time. So the derivative, the move, only acts on H. The derivative V is just this, okay, here and also there. So let's start from these two terms at the beginning. So we have 2 times 2 divided by 8 equals 1/2. And then we have just the move H, the move H. Okay. So the moment we have these on these and these on these. Now we can put all the other terms. So plus 1/8 G squared W move 1 plus I W move 2 W move 1 minus I W move 2. So this is this times this, and then we have to square this times B plus H squared. And then we have the remaining pieces, which is this one and this one, and of course the same object. So this is plus 1/8 I G W 3 minus I G prime D move times minus I G W 3 plus I G prime D move times D plus H squared. Okay. A bit of more algebra. So the first piece remains 1/2 the move H, the move H. Now let's make the problem here explicit. So we have plus 1/8 G squared. And here we have W move 1 times W move 1, this and this, minus 5 W move 1 W move 2 plus 5 W move 2 W move 1 and then plus W move 2 W move 2. Right? And then we have to develop d squared, which is d squared plus 2bh plus plus the other term, which is 1/8 g w move 3 minus g prime, d move, g w move 3 minus g prime d move, d squared plus 2bh plus h. Okay, we have plenty of terms, but let me remind you the scope of this game. The scope is to search for quadratic terms in the fields, because this would correspond to the mass terms of the fields. So let's only consider the quadratic term, or second order in the field. only. Okay. First of all, these two guys talk a lot. So here we have a quadratic term in the W1. Here we have a quadratic term in the W, right? And then here we have two ordered anyway. So here we have 1/8 v squared g squared W1 W1 plus W2 W2 plus 1/8 and all. Okay, for the second part. So these are the only quadratic terms appearing here. Okay. So what we've done here. This is quadratic in W, right? So if we multiply this with a number, it is still a quadratic term. If we multiply this with the field or with a square field, it is not anymore a second order term. It should be a third or fourth order. So we are only interested in the product with that with a number which appears here. Okay, so this is pure quadratic. Otherwise, we would have cubic or even quartic terms in the fields, which we don't need anymore. Now, similarly for the second part, okay, also here we are interested only in quadratic terms. So we only pick up the b here, which is a number. So we have 1/8 v squared, and then g w mu 3 minus d prime d mu g w mu 3 minus d prime d mu. No, sta facendo così. Giusti così, Sammy? Sembra di sì. Sì, perché sono lì a moltiplicare. Okay, so we single out only the quadratic terms in the fields. Now, let me write this one more passage. So this is 1/8 v squared g squared w1 w1 plus w2 w2 plus v squared divided by 8. And here now we have to take the products here, the cross product. So we have v squared w3 w3 plus g prime squared d mu minus g prime w3 d mu minus g prime d mu w. Okay, l'abbiamo fatto. So let me call this term A. Let me call this term B. And consider that all this part here, up to here, have pure quadratic terms in the fields. W1 squared, W2 squared, W3 squared, D mu squared. What is there, what is remaining, are mixed terms. Okay? So these are pure quadratic. And these are mixed. What is the consequence of this? The consequence is that for concerning W1 and W2, we are done. We just have single out quadratic term in the Lagrange. Okay, so it is in a moment we will get the masses. For the W3 and the B, we cannot do it right now because we not only have pure terms but also mixed terms. If you have mixed terms, you cannot derive a physical mass for this object. So we have to work out this a little bit more. Let's first of all concentrate on term F, okay, where we already have the pure quadratic terms. So for the W1, we have 1/8 V squared W1 W1. And for the W2, we have essentially the same 1/8 V squared W2 W2. Right? Now, as we did before for the Higgs mass, since these are quadratic terms appearing in the Lagrangian, they have to be in the form 1/2 MW1 squared W1 W1, and this has to be the form MW2 squared W2 W. Okay. So since once more, since these are now the pure quadratic terms of the W1 and W2 in the Lagrangian, they have to be mass terms in the Lagrangian, so they have to be in this form. And so again, we can now extract the masses. So from this, just by equating the two, we obtain that 1/8 V squared has to be equal to 1/2 mass squared of 2, either 1 or 2 because they are the same. And so we obtain that the mass of the W1, which is the same as the mass of the W2, is the square root of this, so it's 1/2 GV. Okay, so through the unitary gauge, two of the Gaussian bosons have now been translated into the masses of the W1 and W2, which depend on the coupling constant of the charged charge with interaction, and again on the vacuum expectation value of the Higgs field. Okay. Now we are concerned not on W1 and W2, but on the W plus and W minus, so the physical bosons. Right? But the physical bosons, if you remember, are just combination of those two. So W plus minus is the following combination: W1 minus plus W2. Okay. But since the physical bosons are just a linear combination of these two, they have to have the same masses. And so it turns out that the mass of the W plus is equal to the mass of the W minus, so the physical boson, and this must be equal to 1/2 G. This is our second result. Let me remind you that if the potential would have had a shape like this, then the vacuum expectation value of the field would be 0, and so it would be 0, and the mass would be of 0. Okay, so this is not 0 because this potential is like this. So we okay. Now we are halfway. We now have to work out the Z boson and the photon. Okay, so we assign the mass term for the W1 and W2 because they appear as pure quadratic terms, but we cannot do the same for the W3 and the B because they also appear in mixed term. Okay, so we have to do something here. Actually, this both term B we can write in a more useful way. as d squared divided by 8 w 3 d mu. Then we have a matrix g squared g prime squared minus g prime minus g prime, and then we have w 3 and d mu. Okay, you can check yourself that this expression is totally equivalent to this one. Okay, just do the matrix product. And this guy here, let me call M. Okay. Now, this matrix M, that as it will appear in a moment, is a mass matrix. Okay, it is not diagonal, as you can see. Okay, so we have two pure diagonal terms, which in fact corresponds to this and this. But we have also two non-diagonal terms which are responsible for the mixing of the W3 and the B. And this is what we want to remove in order to obtain physical masses for physical bosons. So what we have to do, we have to diagonalize this matrix. Okay, so we have to find a new basis where this matrix is diagonal, and these two states translate into the eigenstate, physical eigenstate. Okay, how do we diagonalize this? By calculating the characteristic equations of the determinant of M minus lambda I is equal to 0, where lambda will be the two eigenvalues. So let's calculate now this. So let's calculate this characteristic equation. So we calculate the determinant of g squared minus g prime minus g prime squared. It is g squared, sorry, minus lambda. Yes, are the eigenvalues here. Okay. What is g squared minus lambda times g prime squared minus lambda minus g squared g prime squared, and this has to be equal to 0. Okay, so it's this times this minus this times this. So what we have here, we have g squared g prime squared minus lambda g squared minus lambda g prime squared plus lambda squared minus g squared g prime squared. So this can go away as we wanted because we are responsible for the mixing. And so we obtain that lambda squared minus lambda d squared plus d prime squared has to be equal to 0. And so in other words, lambda minus d squared minus d prime squared has to be equal to 0. And so we have now two real solutions, right? This is the second order equation. One solution is where lambda is vanishing. Lambda is the eigenvalue, nothing to do with the lambda in the Lagrange, okay? The other solution is where lambda is equal to g squared plus g prime squared. Okay, so once we have now diagonalized our matrix, we are now in a basis where the matrix is diagonal, we can rewrite this expression in the new basis. Okay, so we have to redefine these fields as the new eigenstate of this diagonal matrix. Okay, so this will be, so after diagonalization, b squared divided by 8, I can call this a mu, z mu. Now we have our diagonalized matrix, where the first element is our vanishing eigenvalue, 0. Then it is a diagonal, so we have to take care only to the other diagonal term, which is d squared plus g prime squared. And then again, the new basis is we call mu and z mu. Okay, so now in the diagonal basis, sorry. In the non-diagonal basis, so we have physical basis where the W3 and W2 and the W are mixed, okay? In this case, when now we diagonalize, we have to redefine our eigenstates as let me call just a mu and z, okay? Now, since we are now in the diagonal basis, so in the physical basis, this matrix has to be equivalent. So this expression has to be equivalent to 1/2 mu the mu m squared a 0 0 m squared z mu v z mu. Why? Because when we do now this product here, we obtain exactly 1/2 ma squared mu plus 1/2 mz squared z mu. So what is the logic here? We found this expression here with the mass matrix with the two diagonal elements 0 and d plus squared plus d prime squared. Now, since we are now in the physical basis, okay, so in the diagonal basis, these two objects now have to acquire mass, so they have to appear in the Lagrangian as pure quadratic terms, okay, and this expression is equivalent to this. And so we can now compare the two matrices, okay, and we obtain the mass of the eigenstate A is equal to 0, and the mass of the eigenstate Z, whatever it is when this on top of this. So we have to equate term by term into. So the end will be 1/2 of V root of G squared plus G prime squared. And if we make use of the relation G prime is equal to G and of the theta Weinberg, we can also write in the form GV divided by 2 cosine theta Weinberg. And this is our last result. Okay. So the W1, W2 already appeared as pure quadratic terms. So it was easy, we already immediately determined the mass terms. The W3 and the D were mixed, so we had to diagonalize this matrix, this mass matrix. And so we had to redefine this eigenstate in the new physical basis, where D2 now get a mass. Okay? So whatever A and Z are, the A eigenstate takes a vanishing mass, the Z takes a non-vanishing mass. Okay? Again, function of the multiplication value of the Higgs. Okay, before making the break, let me summarize these results on the slides. Okay, so I'll just summarize what we have seen in the blackboard. So considering all in second order, so quadratic terms in the field, one obtained from the potential energy term of the Lagrangian, the mass of the Higgs boson, square root of 2 lambda times V. From the derivative part of the Lagrangian, okay, we have a pure terms for W1, W2, and mixed terms for the W3 and B. But already from the first two, we can derive the mass of the W's. Okay, so 1/2 GB. And as I was mentioning before in the blackboard, the mass acquired by the W boson depend on the strength of the gauge capping G, but also on the vacuum expectation value of the Higgs field. Okay, and so hence the mass would be 0 in this condition here. So if we would have chosen a mu square positive, okay? So the right solution to provide mass to the boson is indeed the mu square negative. Now, what about the mixed terms? Okay, so this we have to work out a little bit. We have to diagonalize this basis, this matrix, and in the physical basis, we obtain two new eigenstates, A and Z, where A is equal to Z, a mass 0, and Z has a mass which is again function of the vacuum expectation value of the Higgs. Yeah, un po' di pazienza, fatemi concludere questo argomento. So we still have to show that A is the photon and Z is the boson. Okay, for the moment, we are just eigenstate of this matrix. Grazie. Now, up to now, A mu and Z mu are just the eigenstate of the diagonalized matrix, right? Now we can express these in a proper way, so accounting for the full normalization. So if you do this formally correct, you get G prime W mu 3 plus G D mu, and then you have the normalization factor, G squared plus G prime squared. And for Z mu, we have G W mu 3 minus G prime D mu properly normalized with G squared plus G prime. Okay. So of course, the A and the Z eigenstate have to be a combination of those in the non-diagonal basis. Okay, and this is the proper way to write them properly normalized. Now, again, let me remind you that we can always write G prime as G tangent of theta W. And so the AMU, let's just substitute here, is G tangent of theta W, W mu 3 plus G D mu. And here we have G squared plus G squared tangent square of W. So, trivial algebra, it is sine theta W divided by cosine theta W. The G go away. W 3 plus, and then here we have actually 1 plus sine square theta W divided by cosine square theta W. So this is cosine theta W, sine theta W, W 3 plus cosine theta W mu divided by 1 divided by cosine theta W, square root of cosine square theta W plus sine square theta W. Okay. This goes away, this goes away, this is 1. And so it turns out that MU di questo is d mu cosine theta W plus W mu 3 sine theta W. Let's now do the same for the Z. So this is G W mu 3 minus G standard of the weak D mu divided by G squared plus G squared standard squared at W. Again, we can simplify the Proton constant. So this is the W mu cosine theta W minus sine theta W mu divided by cosine theta W, or D divided by 1 divided by cosine theta W, the root of cos squared theta W plus sine squared theta W. So again, this goes away, this is the 1, and so it turns out that we can express the Z eigenstate as minus B mu sine theta W plus B W3 cosine. But now you recognize these two guys, right? It is indeed the electroweak mixing of the W3 and the B, which are indeed the photon and the boson. Okay. Through the theta Weinberg protection matrix. Okay, so indeed, the eigenstate in the physical basis with mass 0 and mass blah, 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 are corresponding indeed to the photon and the boson in the electroweak theory. One more slide and then we do a stop, break. So the eigenstate of the diagonal mass matrix, so the physical in the physical basis, corresponds indeed to these two combinations. So to the mixture of the electroweak masses W3 and B mu, okay, which are indeed the photon and the Z. Okay. So the combination corresponding to the Z0, so this combination here, has acquired mass to the Higgs mechanism, whereas the other combination corresponding to the photon has not. Okay, so the photon remains indeed massless in the mechanism. Just to give you some number, there are also experimental measurements of the mass of the photon. Okay, of course there are only upper limits, and the experimental upper limit to the mass of the photon is 10 to the minus 18 electron volt, corresponding to 10 to the minus 51 grams. And there are also more stringent values from astrophysics, where the mass of the photon is even smaller, so smaller than 10 to the minus 26 electron volt. Okay, so indeed everything is consistent with the photon being massless. Vabbè, dai, pausa. Siamo 10 minuti perché siamo stati un po' stanchi, riprendiamo alle 12:30. Poi dove arriviamo, continuiamo poi la prossima volta. Ok. Ok, ci siamo? Ok. Ci siete da casa? Vedete la slide?
Sì.
Okay. Okay, so let's continue. Let's again summarize our main results. So this picture essentially summarizes the whole discussion started yesterday in a bit more realistic way than the one I showed you yesterday. Okay, so we start with four scalar fields. We start with four massless gauge bosons: the W1, 2, and 3, and the B. Okay, and then we have a Higgs field, which is essentially given by made by 4 degrees of freedom. The W1 and W2 provide a pure quadratic term in the Lagrangian, okay, and they acquire their masses to the H2 and H3 ghost of bosons, which are translated into the longitudinal polarization state, okay, so they become massive. For the W3 and B, okay, again, they are mixed here, okay, but only the Z combination acquires mass to the remaining ghost of bosons, and the photon remains massless, okay. Out of this, we still have a new object, which is the Higgs boson, which is a real particle that has to be found and discovered. So let's now summarize the full Lagrangian, okay, for the Higgs sector in the Electroweak model. So a first term of the Lagrangian is the Higgs term, the pure Higgs term. So we have the kinetic term of the Higgs field and the mass term, which is quadratic in the Higgs. Okay, and by this we derive that the mass of the Higgs is given by square root of 2 lambda b. Then we have the terms for the W's. Okay, so the W1 and W2 pure quadratic terms for which we derive the mass, also the physical W's, 1/2 GB, and the two Yang-Mills terms, so the two kinetic terms. Then we have the Z boson. Okay. Again, we have a mass term here, where the mass of the Z can be expressed in these two ways. Actually, if you substitute to 1/2 GeV here, you get the mass of the W. So this is indeed the relation that we showed last time between the mass of the W and the mass of the Z, which are thus related by the cosine of theta Weinberg. And then we have the Yang-Mills term. And finally, for the photon, we do have a Yang-Mills term, which is the kinetic term, but we have a zero mass. Okay, so this is the full result of our procedure. There is actually one more term here, because if you remember in the blackboard, we only consider the pure second order terms, but we neglect all the other terms, the third and fourth order. These, of course, are there, and they have to be also understood physically. This we will do next. So, as a result of all these procedures, or as a result of the Higgs mechanism applied to the electroweak theory, the W and the Z boson have acquired mass, okay, and the remaining mineral gauge boson, which corresponds to the photon, has remained indeed massless. Now, let's see what about all these other additional higher order terms, so third order and fourth order. Those terms, if you remember now from what you have in your notes, are of this type here. So we have two gauge bosons, either W1, W3, W2, or the B, and then we had the B plus H to the square. Okay, so we have these three possible terms. For our business, for the mass business, we only consider the first one, which is indeed pure quadratic in the field, and then we have just a number here. Okay, and in fact, this term corresponds to the mass terms. Now we have also terms like VBH and VBH squared. And this corresponds, as you can imagine, by the interaction of the gauge boson with the Higgs field, Higgs particle, actually, the Higgs boson, or the interaction with two Higgs bosons. And you see here the corresponding interaction vertices. Okay? So this is the way the gauge boson interacts with the Higgs field, and it is indeed the way they acquire mass. Now, using the relation that relates the physical W's with the W1, W2, and the definition of the coupling for the Z boson, okay, we can write down these terms here in the Lagrangian in this simple way, okay, where we have the pure quadratic, we are now considering this guy here. Yeah. So we have now the quadratic term times the Higgs, quadratic term times the Higgs, quadratic term times the Higgs, okay? And by with simple algebra and by remembering the definition of the Z coupling constant, the couplings for these three terms are given here in red. Okay, but this coupling cannot be translated into the masses. Okay, you can just go back to this slide here, okay, and see that these couplings here correspond exactly to the masses. Okay, times G times the coupling constant. Okay, so the first term where the W minus interact with the Higgs bosons are weighted by G and MW. The second term where the W plus interact with the Higgs boson is weighted by G and the mass of the W again. And the last term where the Z boson interacts with H is given by GZ MZ. Okay. So the important message here, the thing that you have to remember is that the coupling of the bosons, the gauge bosons with the Higgs field are proportional to their masses. Okay. The heavier the boson, the more intense is the interaction with the Higgs field. The lighter the boson, the less intense the interaction. For the case of the photon, there is no mass, and so there is no interaction at all with the Higgs field. Okay. So the Higgs mechanism allows to associate massive particles to some of the gauge fields without having explicitly introduced a mass term in the Lagrange, which is an operation that would have broken the gauge invariance of the Lagrange. We didn't put by hand the mass term. Okay, the mass term arose naturally through the Higgs mechanism, so through the spontaneous symmetry breaking of the Lagrange. And together with the now massive electroweak bosons and the photon, a new object appears, which is the Higgs boson with a non-zero mass. Okay. Now let's concentrate on the mass of the Higgs boson. Okay, so it is square root of 2 lambda b. Now b is a quantity which is the vacuum expectation value of the Higgs boson that we can actually calculate, because b, if you see here, it is related to the mass of the W, which we can measure, and it is related to the mass of G, we can calculate. So we can actually extract the value of B, which is something like 246 GeV. Okay, so we have a precise prediction for the vacuum expectation value of the Higgs field. What we don't have, and what the standard model does not provide, is the value of lambda. Lambda is a completely free and completely unconstrained parameter in the standard model, and this means that the mass of the Higgs itself is a completely unconstrained parameter of the Higgs model. There is no way the standard model can predict the mass of the Higgs boson. The only way is to search it and find it experimentally. Okay. Now we discussed about the masses of the gauge bosons. Okay. What about the fermions? Electrons, muons, quarks. We know that they all, of course, are massive. Okay. Let's for the moment forget about the neutrinos. Let's consider a charge of electrons and quarks. How do they get mass? So let me make some simple consideration here. Let's consider as an example the mass term for a generic fermion in the Qcd Lagrange. So this is the Qcd Lagrange that we derived a long time ago, now for a generic fermion. Okay? So we have the kinetic term, the mass term for the fermion, the interaction term of the fermion with the photon field, and then again the mix term, so the kinetic term of the photon. Now, let me make a short derivation. So let's focus ourselves on the mass term of the fermion in the Qcd Lagrange. Which is minus m. Grazie. So for a generic fermion, there could be an electron, could be a quark, whatever, but not neutrino. We have the mass of the fermion, then we have the adjoint spinor of the fermion, and then the fermion. This is the mass term, right? The standard one we derived 3 months ago in the Qcd Lagrange. Now, this we can always write as mf f bar f, where something is equal to 1, which we can write as 1/2 1 minus gamma phi plus 1/2 1 plus gamma. This is just 1. You can see immediately. So what we do here is to write this as minus f adjoint But here we recognize now the left and right chiral operators, projectors, right? So this is the P left plus P right. And then, as we know, we can always decompose any spinor into its right-handed and left-handed component. So this we can write as Fl plus F. Now let's take all the products. So this is minus F R, and now we have PL FL plus PL F right plus P right F left plus P right F right. Okay. Now, when you apply the left projector on a right spinor, you get the zero overlap. And similarly, when you apply the right projector on the left spinor. There is nothing to project in the direction because it is a pure left or a pure right. So this is simply minus M F bar, and then we have the PL FL plus P right F right. Let's now put the adjoint spinor into the game. So this is minus MF, and this we can write as adjoint L FL plus F adjoint P right F right. And now we let the projection acting on the adjoint spinor. Okay. And let me remind you that if this is an adjoint spinor, then the left-handed projector projects the right-handed adjoint spinor, and the right-handed projector projects the left-handed adjoint spinor. This is the component for the adjoint spinor. So this is minus and F bar L F L plus F bar L F L. Okay, so here we have the product of right and left final spinors. Now let's comment this on the slide. So in other words, the mass term for any Fermi in the Qcd Lagrangian can always be written in this form here. Okay. Now this is completely fine for Qcd because Qcd is completely democratic with respect to left and right Fermis. Okay. This we know. Of course, this is not the case for SU2L, for the charged current, because we know that charged current only interact with left-handed fermions and right-handed antifermions, but not vice versa. Okay. So this kind of combination here, okay, when put into the Lagrangian of the Electroweak theory, this will immediately kill the gauge invariance. Okay, so this term can stay in the Qcd Lagrangian, but cannot stay in the Qcd Lagrangian, but cannot stay in the Electroweak Lagrangian. So in other words, in the standard model, also quarks and leptons have to be introduced as massless particles. Okay. So before Higgs, everything is massless. Not only the gauge boson, but also the fermions. Now, the fundamental point here is that it can be shown that the Higgs mechanism also provides the masses to the leptons, to the fermions. So not only to the gauge boson, but also to quarks and leptons. And this is encoded in the so-called Yukawa sector of the Higgs Lagrangian, okay, which is given here. We will not derive this, okay, but it is in this form here. So we have essentially the same term that I derived in the blackboard, okay, times the vacuum expectation value of Higgs, and a similar term, but now multiply with the field, which is the Higgs field, okay? So how can we interpret these two objects? The first term really is the Fermi mass term, okay? But it is now introduced not by hand, because this would, as I said before, would kill the gauge invariance. but it is introduced in a gauge invariant way, so through the Higgs, through the interaction of the Higgs field. In fact, the mass is proportional to the Vacuum expectation value of the Higgs, to V. Okay, so this is now possible, and so through the Higgs, through the interaction with the Higgs, also fermions acquire mass in a gauge invariant way. The second term, where now the mass, these objects are now convoluted with the Higgs field, is clearly an interaction term, where the fermion interacts with the Higgs field. Okay, so we have in this Yukawa sector of the Lagrangian a mass term, a gauge, say, a gauge invariant mass term for the fermion, and a fermion Higgs interaction term. Okay. Now, if you compare this expression with the one that I have in the blackboard, of course, the coefficient here must be the mass of the fermion, right? All the rest is the same here. So the mass of the fermion is given by this expression here, okay, which is again once more function of the Vacuum expectation value of the Higgs field. And one can also invert this and extract this GF coupling constant, which is the coupling of any fermion F, with the Higgs field. Okay, so this GF constant gives you the intensity of the interaction between any fermion and the Higgs field. And if you just invert this formula, you find that this coupling is proportional to the mass of the fermion. Okay, so again, heavier fermions interact more intensively with the Higgs boson, lighter fermions less intensively. Okay, so in other words, the electron, which is a very light particle, has a very, very mild interaction with the Higgs boson. The top quark has a huge, very strong interaction with the Higgs boson, okay? Because the coupling is proportional to the mass. And so this Yukawa term in the Lagrangian, we can write down this term, okay, as a pure mass term, but now gauge invariant for the fermion, and an interaction term between the fermion and the Higgs field, which is where the coupling is proportional to the mass of the fermion. So we can conclude that the Higgs field would couple preferably to the heaviest fermion, which are kinematically available, and vice versa, the heaviest fermion, for instance, the quark top, are those that interact more intensively with the Higgs field. Okay. One additional comment here. What about the mass of the proton? Okay, so the proton is an up-up-down object. Okay, in the simplest scenario. So the mass that the up quark and the down quark receive by interacting with the Higgs field is very small. Okay, this is the bare mass of the up, which is just 2.3 MeV for the up quark and 3.8 MeV for the down quark. This is the bare mass of this light quark, and this is the mass that they indeed acquire by interacting with the Higgs field. So in the proton, we have 2 up quark and 1 d quark. So let's just add up the masses, and we are obtain something like 9.4 MeV, which is only 1% of the mass of the proton. And this is really remarkable. This means that the 99% of the mass of the proton, and so the 99% of the mass of atoms and molecules and matter and universe, whatever, does not arise from the Higgs mechanism. The Higgs mechanism provides the masses of the elementary particle only, but the proton, which is the core of atoms, molecules, and matter in general, is 99% made by something else. And this something else we already studied, which is the Qcd vacuum. Okay? Inside the proton, we don't only have up, up, down, but we have up, up, down, immersed into a crazy sea of gluons, which are emitted, which radiate, which split into Q-Q pairs, which emit gluons, etc., etc. All the energy encoded in this Qcd vacuum provides the 99% of the mass of the proton, and let me say, of the mass of matter that surrounds us. Okay? The Higgs mechanism is fundamental. Without Higgs mechanism, the gauge boson would be massless, okay, and also the heavy electron. But the heavy electron, who cares? In our life, we never have to do with a tau electron or with a top quark. This can only be produced in a very energetic cosmic ray interaction with the Earth atmosphere or in an accelerator in a laboratory. Otherwise, we are only dealing with the first families of the fermions, which are light. So that's an important point. And now we can draw the full picture of the standard model. Okay, this I showed already you in the very first lesson, and now we are back here. So we can divide all the elementary particles into two main sectors: the matter particles, which are those that constitute the matter, and the gauge bosons, which are the mediator of the forces. So the leptons are either charged and neutral. Let's for the moment forget about neutrinos. This will be studied next week. Charged lepton interact either electromagnetically and also through the W and the Z, so weakly, in neutral current and in charged current. The quarks do the same because they have electric charge, so they interact electromagnetically. They also interact weakly, as we've seen, through the Z and the W, and they can also interact strongly with the gluons. The SU3 color is a non-abelian theory, so the gluons carry color charge, so they can interact themselves. Okay. Similarly, the W can interact itself because it does carry weak isospin, okay, which is the weak charge, so it can also interact, and also W and Z, of course, can also interact, as we've seen. We've seen that the vertex between the Z and the W is the one you need to recover the unitary violation, okay, in the cross section. Finally, all the massive particles, so all the charged leptons and quarks and the W and the Z interact with the Higgs. We don't have any connection between the photon and the Higgs and the gluon and the Higgs, because those guys are massless. And finally, since the Higgs is massive itself, it can also self-interact through triple and quadruple vector interactions. Okay? Is that clear? Now, a bit of history. So it was 1967 when Weinberg realized that the Higgs mechanism could provide the mass not only of the gauge bosons of the electroweak interaction, but also to the fermions, the way we just show in the black book. Okay, so he then had the idea to integrate the original electroweak model, which was proposed before by Glasgow, with massless electroweak bosons with the Higgs mechanism. Okay, and he presented for the first time a comprehensive electroweak theory where the W and the Z and also all the fermions except the neutrinos acquire mass through the Higgs mechanism, and the photon remain massless. Okay, and then a similar approach was also undertaken independently by Salam 6 months later. Okay, and this is indeed how the standard model was born in that year, and all these three guys got the Nobel Prize. Okay, a few years later for this. There was still some missing proof for the standard model to become a real physical theory. And the proof is that that was missing at the time is that it is a renormalizable theory. We are studying renormalization in the QED sector, but this applies to any gauge sector. Okay, a theory which is not renormalizable, so a theory which provides infinities, okay, is clearly a non-physical theory. So it can only be an approximated model or even something wrong. In order for the standard model to be the theory, it has also to be renormalizable. And the renormalization of the standard model, so the electroweak interaction, was proved only in the early 70s, so years later, by Gerhard Vogt and Martin Bergman, okay, who also got the Nobel Prize for this huge effort. It was an extremely complicated proof, but it is now there. Okay, so it is not proved that in general spontaneously broken Young's theory, such as the standard model, are by construction renormalizable. Okay. So the theory was there, let's say, by the first part of the 70s. Now, everything is perfect, is elegant, is fantastic, but if you don't find the Higgs boson, it cannot be just a fake, right? So now the challenge was indeed to find the Higgs boson, because the discovery of the Higgs boson with the properties of the Higgs boson predicted by standard model would be the final proof that all this mechanism is indeed real. And for the experimental community, it took like 10 years after the Higgs model was proposed in 1964 to really realize that there had to be a new particle, a new scalar particle with a non-zero mass that had to be discovered experimentally in order to complete the picture of the standard model, okay, the puzzle of the standard model. So the standard model, the Higgs boson in the standard model is a neutral scalar particle. So the charge is 0 and the spin is also 0. Okay, and so being a scalar particle, it has no polarization for vector in its definition. So you can just describe it as a plane wave. Okay. The mass, as we've seen, is a function of the vacuum expectation value of the Higgs, which is a number, 246 MeV. So this we can calculate, but we don't know nothing about the lambda parameter. So it is completely unconstrained from the theory side. How does the Higgs couple to other particles? This we have also discussed before, okay? It does couple to any essential particle that has mass, except neutrinos, where the coupling constant of this interaction is proportional to the mass itself of the particle, either Higgs bosons or leptons and quarks, okay? And so the Higgs boson, the real Higgs boson, can decay into any of these objects, massive objects, okay? So for instance, the decay of the Higgs boson into a fermion-antifermion pair is depicted here, where the coupling constant is proportional to the mass of the fermion itself, okay? And so it is possible for any pairs of fermion which allow energy conservation. So the Higgs cannot decay into top antitop because the top is too heavy, also for the Higgs. In each case, the matrix element is proportional to the mass of the particle coupling to the Higgs bosons. Okay, and so the largest branching ratio are, of course, corresponds to the most massive particles. So this is how the branching ratio for the decay of the Higgs boson vary as a function of the mass of the Higgs. Okay, suppose we don't know yet the mass of the Higgs. So before 2012, this was actually not known, and this is the way the branching ratio of the decay of the Higgs into different final state depends on the mass of the Higgs itself. So you see here that if you make an hypothesis of a Higgs mass of 125 GeV, which is indeed the Higgs mass that was discovered, okay, then we can make a zoom here in this region that you see here in this other plot. Okay, so we are zooming here around 125 GeV, which is indeed the mass of the Higgs boson. Okay, and what you see here is that the most probable decay of the Higgs is in BB bar. Okay, TT bar is not possible because of energy conservation, so the next in the list is BB bar. Then there is also a large probability to decay into WW. Okay, but the mass of the W is 80 GeV. So the mass of 2W is 160 GeV. That is heavier than the Higgs boson. So this in principle could not be possible, but it is still possible if one of the two W's is virtual. Okay. So the Higgs can also decay into W pairs, but only if one of the two is virtual, so is off shell. And then you see here the hit parade, okay, for the decay. So the first is the BB bar with a probability of almost 60%, the W is a probability of 21%, then the tau, the gluon, the Z, etc., etc. Now it is interesting to see, and you see also here, that the Higgs can also decay into massless particles. How is this possible? How can the Higgs decay into 2 photons or into 2 gluons? Well, as you can see already in the bottom of the slide, this is possible through loops of heavy fermions. So for instance, through top quark, which is the one that most interacted with the Higgs. Okay. So only through these loop diagrams, the Higgs boson can have in the final state either 2 gluons or 2 photons, which are massless. Okay. Or you can also have a decay like this, where the Higgs split into a W plus, W minus, okay, then you have a loop of W's at the end radiate 2 photons, okay? So it is also possible to have in the final state neutral particles as a result of the Higgs decays, but through loops that involve heavier particles, of course. Now, the experimental search for the Higgs boson started many decades ago, okay? But the discovery, as you know, appeared only in 2012 at the Hadron Collider. And up to the time, only upper limit could be set to the mass of the Higgs, okay? Because the energy of the accelerator that were available were not enough to reach the Higgs mass or to have enough statistics to produce the Higgs mass, okay? So the two main contributions were given by the LEP, okay, which was operating in the 90s, where they found a lower limit for the Higgs mass of 114 GeV. So this was the maximum that they could explore of LEP. And they didn't find anything. So the mass of the Higgs must be at least 114 GeV. Then, when LEP was closed for the construction of the Hadron Collider, then the Americans started the search of the Higgs at the Fermilab, at the Tevatron, the proton-antiproton collider that where the top quark was discovered, if you remember, that we discussed yesterday. But still, the machine was not really able to find the Higgs. They could anyway put another limit, okay? So they essentially exclude the mass of the Higgs to be larger than 156 GeV at a 95% confidence level. So let's say after the era of the LEP and of the Tevatron, and from before the starting of the Large Hadron Collider, there was essentially a tight window of possibilities for the mass of the Higgs, between 114 and 156, with a 95% confidence level. Okay, so people, when the Large Hadron Collider started, were already somehow aware where to search for. Okay, so it was actually in a narrow mass window. How can we produce Higgs at the Large Hadron Collider or at any hadronic collider? At the collider, we have proton colliding. So at the elementary level, we have either quark-quark or gluon-gluon. Okay, and it turns out that the most efficient way to produce the Higgs boson at the Large Hadron Collider is through the so-called gluon fusion that you see here. So we have one quark from one colliding proton, one quark from the other colliding proton. The two radiates a gluon. The two gluons form a loop of top quarks where the Higgs boson is finally produced. Okay, so it's a rather complicated process, but it is the most efficient way to produce Higgs bosons at the Large Hadron Collider. Another concurring process is the one here, is the so-called vector boson fusion, where the two colliding quarks radiate a W, and the W merges into Higgs bosons. Then there are also less efficient processes, like the so-called Higgs-Strahlung, where essentially you have a quark-antiquark resulting in a W or a Z, and then either the W or the Z radiates a Higgs boson, like the electron that radiates a Bragg-Strahlung photon. Okay, and this was the most efficient process at the lab. Another process is the associated production of the Higgs with the pairs of top quarks, and this has also been observed at the Large Hadron Collider. Okay, and finally, another process is the associated production with a single top quark, but this has not been discovered yet. Okay, people are searching for this channel, but it's not discovered. So at the Large Hadron Collider, you see here now the cross-section in picobar. Okay, the cross-section becomes relatively large only for the gluon-gluon fusion process. Okay, where the two gluons fuse through a top loop into the Higgs. Okay, then the vector boson fusion has a much smaller cross-section, and even less for the other mechanism that I just showed before. Okay, and you see also these into this table. So here we have the Tevatron at almost 2 TeV in the center of mass, and the Large Hadron Collider at different center of mass energies, 7 TeV, 8 TeV, 13, and 14. And here you have all the possible, the main, let's say, production mechanism for the Higgs. Okay, the Gluon fusion, vector boson fusion, associated production with the W, associated production with Z, and associated production with the top pairs. Now, what the numbers tell you is that if you look now at the Gluon fusion, the cross-section values, okay, are much, much larger at the Large Hadron Collider than for any of the other mechanisms. Okay, so indeed, the Gluon fusion is the dominant mechanism to produce Higgs bosons at the Large Hadron Collider. And the other observation, if you look now at the total cross-section, you see how it rises quite fast with energy. Okay, so despite you only need 125 GeV to create a Higgs boson, the higher energy you can provide the center of mass for the collision, the higher the probability to produce Higgs bosons. The cross-section for the production of Higgs boson in the proton-proton collision, okay, is given here. Okay, is given in terms of the elementary gluon-gluon fusion cross-section, so the gluon-gluon into top into Higgs. But as you understand, this has to be convoluted with the probabilities to find the gluons with the proper X-Bjorken value into the two colliding protons. So essentially, this cross-section is a convolution of the elementary gluon-gluon fusion into Higgs times the Parton distribution function of the gluon in the first proton times the Parton distribution function of the gluon in the second proton, because this tells you the probability to find the proper gluon to have the Higgs at the end. Okay, so knowing and measuring the gluon PDFs is crucial not only by itself but also for measuring the cross-section, the production cross-section for the Higgs. And just to give you some number, the cross-section value for the Higgs at a mass of 125 is of the order of 20 picobars. Now, the ATLAS and CMS experiment at CERN searched for the Higgs boson in many different decay channels. Okay, but at the end, the discovery appeared in these two channels. So the Higgs into 2 photon and the Higgs into 2Z, which at the end decay into 4 charged electrons. Okay, so for instance, 4 electrons, plus minus, or 4 muons. Why those two? Clearly, they are not the highest, do not correspond to the highest branching ratio. The highest branching ratio is for the BB bar, if you remember, 60, 70%. But these are the cleanest. Okay, so you want to find a very small signal in a huge background. And so, at the end, the choice was to look for the less probable decays with a small branching ratio, but for the most clean events. Okay, and this indeed brings to the discovery of the Higgs. So you see here one of these events at the CMS. This is the event where the Higgs decays into 2 photons, and you see the release of the energy release of these 2 photons into the calorimeter of the CMS experiment, which surrounds this tracking detector. And this is an analog decay in the Atlas detector. Okay, in this case it is a Higgs into Z virtual Z, which goes into 4 electrons, and you see here the 4 electrons through the energy that they release in the calorimeters. Okay, so this is, as you see, it is clear. There are no jets. It is all clear here. Okay, it's a very clear event topology. And so these are now the discovery plots. Okay. So this is the Higgs into 2 photons, and this is Atlas data. So this is essentially the invariant mass of the 2 photon system, and you see that at a certain point they found a little bump here, okay, at around 125 GeV. And if you look now the difference between the data and the background, you see that the bump is quite visible here. Okay. Similarly, they also provide similar results also in the ZZ decay, so in the 4 muon, for instance, where they found indeed a peak, a small peak. The numbers are very small here, okay? A small peak in the invariant mass of the 4 muon final state, okay? And the two happen to be at the same mass, 125 GeV, okay? So the discovery of the Higgs boson was announced at CERN by the Atlas and CMS experiment. It was July 2012. You see here the main auditorium at CERN, which was filled, and people actually, when it was announced that a big discovery was done at CERN, people was sleeping in the stairs beyond this room the night before, just to have the possibility to enter the room in the morning and to have a seat for the announcement. So who you see here, a lot of people from CERN. Hoyer, who was the general director of CERN at that time, in 2012. Then I think it is in Candela, was the spokesperson of CMS, and she's Paola Zanotti, who was the spokesperson of the ATLAS experiment, and who is now the CERN general director. Sitting somewhere here was also Peter Higgs, who was invited for the announcement. They didn't tell him that it was about the Higgs boson, but it was clearly obvious. He was called on the phone and they said, look, Peter, it is better that you come at CERN because otherwise you would penitentiresti on the end. And that's not at all. Okay, so a lot of passion here. This was indeed the event where the Higgs discovery was formally announced at CERN. There was also streaming direct. And 2 years ago, it was 19th of May, okay, it was the birthday of Higgs, and Fabiola Gianotti, so he's now the CERN director, wrote him this message that I want to read you. So happy birthday, Peter, and many happy returns to CERN. So the mechanism that you and Brute and Francois Englert first described in a landmark paper in 1964 has been a guiding thread of experimental particle physics for decades. The Brute-Englert-Higgs mechanism is a triumph of the theory, and its confirmation by the Atlas and CMS experiment is a monumental achievement. Okay, so indeed, with the discovery of the Higgs boson in 2012, the standard model is complete. Okay. Few numbers just to conclude. The mass of the Higgs boson measured by the 2 experiments is here reported. Okay, at the time of the discovery, so with a relatively large uncertainty. Okay. But nonetheless, the precision was enough to be above 5 sigma. Okay, so indeed they could claim the discovery. It was 5 sigma. The Higgs boson was the last missing piece on the standard model. Its discovery in 2012 concluded 50 years of search. The article from Higgs and friends were in 1964. So 48 years of hunt for these bosons, and clearly Higgs and Hengler got the Nobel Prize for this, okay, with the motivation that the theoretical discovery of a mechanism that contributes to the understanding of the origin of subatomic particles. Brute, unfortunately, died the year before, and so the Nobel Prize can only be given to live people, okay? So unfortunately, miss it. So this was the situation in 2012. Of course, the search is continuing. Hadron Collider is continuing to take data, and this is now a more updated situation in 2020, where now you see the significance of the peak is much higher in both channels. This is still the 2 photon, this is still the 4 lepton channel. Sorry, here. Okay. Here you see now the mass values of the Higgs, okay, for different measurements of the Hadron Collider. So separately from the 2 experiments, from the 2 different final state, photons and 4 lepton, and for run 1 and run 2 Hadron Collider, and also combined measurement between alpha CMS for the photon and alpha CMS for the 4 lepton, and all together here. So the width of this blue band here is the global result of alpha CMS combining all the 2 final state decay and for the run 1 of the Hadron Collider. Today we know the mass of the Higgs with a higher precision, so now the error is down to 0.14, and the mass is indeed 125 GeV with a width smaller than 0.014 GeV. The last slide, as I showed before, the BB bar decay mode is the most probable, is the one with the highest branch inversion, okay? But it is also a dirty event, because when you create quarks, you create jets, and you have jets not only from the signal, but also from the background, because you are smashing 2 protons into quarks and all fragment into jets, okay? So it is very difficult to find out this signal. This was actually found in 2017, so 4 years ago, by the CMS, okay? So the event is a proton-proton that goes into Z plus X, where the Z goes into electron-positron and X indeed into BB bar. You see also here the event display. So these are the 2 electrons from the decay of the Z, and these are the 2 B jet from the decay of the Higgs. Now the question is this real signal from the Higgs, or can be BB bar from a vector boson? Also the Z can become BB bar, right? So here you can compare the data, which are the point, with either this gray histogram, which represents only the production of ZZ and WZ, or the, I don't know, red, I think it's red, or the red one, which includes also the possibility of W, X, and ZX. And in fact, the data match with this second hypothesis. So indeed, these BB jets were coming from the decay of the Higgs. Okay? Now, to conclude, the probes for the production of the Higgs at the Hadron Collider are those that I was mentioning before: Gluon Fusion, Electroweak Fusion, Higgs stratum from the Z and the W, and associated production with the top pairs. And these are all checked experimentally. What is still missing is the associated production with a single top. Concerning the decay modes, okay, not only the W, the Z, and the B, but many of them have already accomplished. So the photon, Z, W, tau, tau, BB. There is also evidence for mu and Z photons, and people are still searching for decay of the Higgs into these still missing decay modes: the charm, meson, and electron. Okay, let's stop here. Sorry, I was a bit long today. Ok, con questo abbiamo concluso il modello standard. Okay? Ci vediamo settimana prossima, dunque il 2 è festa, quindi ci vediamo noi giovedì 3, qui per l'ultima lezione in presenza, parleremo di oscillazione dei neutrini, e il giorno dopo, il 4, alle 3 di pomeriggio, come abbiamo detto, faremo l'ultima lezione in streaming, quindi tutti a casa, e parleremo di Physics Beyond Standard Model. Okay? Metto poi un annuncio sulla classroom. Fisica oltre il modello standard.